Okay. So I am Ankush Deshmukh. So presenting some methodologies to calculate the interfacial energy based on some molecular dynamic simulations. So here I have present. Hello. Okay. Little bit of. Okay. Okay. So I am presenting some methodologies to calculate the interfacial energy based.
So until now what we have seen is what you need, how a calculation model is to be created, what are the essential ingredients that we need, right? So you need your thermodynamics that you saw in the last lecture. And in the thermodynamics, as I said, difference of effect is very important. One part of the difference of effect is the light formula, which is coming from the HC. The second part, which is important, is in getting the connection with the thermodynamics and the correct is the interfacial energy, because that is again part of the difference. Right? First, one of the parts is what's covered by thermodynamics. The second part is the this is typically increased from experiments or lower level scale calculations as we review. Okay, so basically how you compute these properties, consider again the quantity for unexpected material, alright?
So here I am presenting some methodologies used to calculate the interfacial energy. So I have echoes here. Is it? I have echoes in the systems. Yeah. Okay. So I'm presenting few methodologies to calculate the interfacial energy based on some molecular dynamic simulations. So these are our collaborators and some funding agencies. So interfacial energy is basically the fundamental property that influence many properties others, that is microstructural evaluation, phase transitions, phase transformation, and some mechanical properties including also corrosion and alloy behaviors. So which affects the solidification patterns, precipitation, strengthening of the high performance alloy, which in different applications ranging from aerospace components to other medical applications also, to uh, uh, making the medical devices. So based on this interfacial energy, it is that interfacial energy used in microstructural phase field simulations, which is one of the input parameter to this phase field simulation. Uh, so we use this understanding this interfacial and controlling that interfacial energy is essential for tailoring the alloy performance for specific applications. It is also important because to calculate the reliable value of interfacial energy is also important, because the interfacial energy which affect various other parameters during the simulations. So here we choose the system that is copper lead system, for which the experimental interfacial energy is available, which will for our case. So to verify the different methods to calculate the interface energy. So we use the copper lead system, and one another example is also there, that is aluminum and lead systems, different orientations. So we will discuss about the copper and its alloy systems.
Not yet in the doc format. What Sankara had
So
asked.
here we choose three different structure to model the interface. So first one is the interface structure with vacuum. So there is no periodic repetitions along one directions. And second one is the interface structure which has a periodicity in all three dimensions.
Not able to figure out how to put these things. And in this proposal, it is not mentioned as
General experimental procedures, right? So it is the copy of the experimental procedure in which the small nanocluster of one of the solidified rock which is put on the substrate of the any materials. So here in copperless system we have the substrate as a copper and the solidified rock is as a PP
I'll do it
material.
today. I'll
So
send this today and cover
So in,
letter means you have to just write.
in some cases, we calculate the interface energy as a total energy of the interface minus the individual total energy of the each surfaces. So that gives the interfacial energy. So here we have two types of interface. I have used for some four methodologies. So one in type 1 we have the non-periodicity along one directions, and in type 2 we have the all periodicity in all directions. Periodicity in all directions. So method 1 is basically the static calculation which is not dependent on any temperature. So the no vibrational modes are active in this calculations. So the total energy is basically the potential energy of the systems. And in method 2, that is we can calculate the total energy of the system at temperature T.
File and I send that file.
So the structure of type 1, which I have already told that there is no periodicity along one direction. So the two directions are periodic. So and type 2 also there is all periodicity in all directions.
And but there's somebody else from their head office.
So the method 3, we use the vibrational free energy methodology.
No, I didn't mark them, but IT and good people send it to all these people. So they goes to Sankara, to Director DMRL and to the Delhi head office, somebody there,
Okay. So in method 3, we use the vibrational free energy method, which is based on some Vetas Rodriguez methodology they developed to calculate the free energy at finite temperature T. So and using the type 2 structures. So in methodology 4, we use the Helmholtz free energy, which is calculated at finite temperature using same type of interface structure. And in methodology, we will discuss, that is the second figure, which shows we have some nanocluster drop which is solidified at finite temperature and which is placed at the substrate of the one of the material. So we will see the method first, which is the static calculation. So to calculate the interfacial energy, we use calculations where A interfacial is the total energy of the interfacial, which includes here the potential energy as a total energy of the interface system, and E bulk is the surface total energy. This is also the all energies are the potential energy because it is static calculations. So EC bulk is the total energy of the C material. Similarly for D, and sigma EC and sigma D is the surface energy of the given surface of the individual material. So and A is the interface area. So to calculate the surface energy, we have the formulations. So 1 by 2 is basically the two surfaces at the interface, at the surface. So we will see in later slides how the surface looks like. And each surface is the total energy of the surface. and NS is the number of atoms in the surface slab. Whatever the number of atoms in surface slab, that is that number of atoms. And E bulk is the total energy of bulk surface. If it is copper, then the bulk energy per atom of that copper surface, copper material, which is bulk 1. So based on this methodology 1, we have calculated for different materials, but some material gives some reasonable value, but some cases it is unreasonable. So this methodology will not be applicable to most of systems. So we check the methodology 2. So in which we have the non-periodic simulation cells from which the interface is generated, and we calculate the interface energy based on this interface structure. So here is also the E vacuum is the total energy of the interface system, and individual E vacuum and EPB and E copper is the total energy of that systems, but it is at finite temperature. So that total energy contains potential energy plus kinetic energy, which that kinetic energy contains additional smoke. So it gives the reasonable value for this case of copper 001 and PB 001 surface, which is compared to the experimental value. So experimental value is 926 millijoule per meter square, and your calculated value gives 686 millijoule per meter square. So during these calculations, I have calculated some mismatch depending on the temperature for each systems, and here is the thickness of the simulation cells. So it is about that interface structure has a thickness of around 10 nanometer, and this is the orientation relations and number of repetitions I have used to generate the interface structure for each from the surface of each slab. So I have calculated the interface energy using methodology 2 and type 2 of structure. So here the interface structure is periodic in all directions. So using that methodology, I got the interfacial energy. So with respect to in the experimental value, I got the reasonable value, that is 229 at 0 bar pressure, and 1 bar pressure it is 724, which is reasonably close to the experimental value, but it is not giving for correct value for others orientation of material for the same other orientation of the interface for the same material. So though the difference is at 583, it is 197 millijoule per joule per meter square. So, but the temperature at each temperature, the interface energy is small value and some not a correct trend we have observed here, because the at temperature increases, generally interface energy goes down, but it does not look here. So the method 2, I have calculated, I have used to calculate the interface energy for copper 00 and PB, which gives, so the experimental values, that is type, if I use the type 2 structure of the interface, I got some reasonable value close to the interfacial energy for this orientation of the material. So the methodology 2 has some disadvantages and advantages. So it requires smaller length and time scale calculation, because it is you can simulate the structure within few number of orientation, but it depends on how much lattice mismatch you want to minimize. according to that, the simulation cell increases. So, but the drawback is we have the large lattice mismatch depending on how much repetitions you have repeated to minimize the lattice mismatch between two surfaces to construct the interface. So in this case, it may not be possible to reconstruct the interface layer and locate it properly, which is in realistic conditions. So we have also studied the methodology 3 to calculate. So by using methodology, I have calculated the interfacial energy for copper 001 and pupillate 001. So here in this methodology, I calculate the interface energy using vibrational free energy, which does not contain the configurational part of the system. Here only I have considered the vibrational part of the systems. So based on this formulation, I got the interface energy which is negative, which is not correct at all. So so this vibrational free energy I have calculated. So here is detailed methodology to calculate interface energy based on the. So the total free energy is basically the combination of vibrational free energy and configurational free energy. So we will discuss about first vibrational free energy, which is formulated as based on three terms basically. The first one is the harmonic contribution that of the free energy, which is from reference systems, and second term is gives the irreversible work done and in forward direction and forward to back directions. So two directions we have divided it by 1 by 2 to cancel out. And second term is third term is the correction added due to the center of mass correction of the system. So that is three terms which is included to calculate the vibrational free energy. And this methodology is known as Frenkel-Lab method to compute vibrational free energy part of the systems. So in case, so it is simple, much simple for calculating the interface vibrational free energy for a single component system, but it is in binary. Then we have to consider the compositional contribution in a harmonic term. So we have see the concentration of each elements, or you can say the material. So this is the component-wise harmonic free energy, and relative terms are there. So, and second term is the irreversible work done. It is calculated using the thermodynamic integration with forward and backward integration, and to and third one is the free energy correction due to the center of mass of the systems, which is calculated with this terminology. And altogether we have added all three terms and to get the vibrational free energy of the systems. So to get this free energy, we need some prerequisite, that is the spring constant. Based on this spring constant, we use we calculate this spring constant. So to get this spring constant, I have the relation that is k equal to 3 kbt over, that is mean square displacement of the system. So mean square displacement can be calculated here, that is average over x final initial its final position minus initial position along each directions for each given atom. And fourth methodology, we have used the Helmholtz free energy. Based on Helmholtz free energy, we have calculated the interface energy by using the type 2 structure, which is periodic in all directions. So here also three terms. So first one is can be calculated analytically, and second term, that is delta A1 and delta A2, we need to compute with some formulations. So delta A1 is basically the difference between ideal Einstein crystal and interacting Einstein crystal, which is given here. That is U lattice minus 1 by beta. Beta is 1 by kBt, and log of exponential of minus beta into U solid, that is potential energy, minus U lattice, which is average forward. So it is Einstein crystals, ideal Einstein crystal. And delta A2 is the difference between the interacting Einstein crystals and real solid. The real solid is basically we are simulating molecular dynamically, and it is given as minus 0 to lambda E. So lambda is basically the maximum wavelength, that is constant here basically, and it is average over each atom from I to n number of atoms, which is from initial position to the final positions. That is clear. And it is all simulations are done at constant temperature, volume, and number of particles, that is NVT ensemble. And delta E lambda E dash is the maximum spring constants value at which the integration is done. So lambda is basically the thermal wavelength, which is computed as h by under root 2 pi m kBt, and lambda is the spring constant I have said earlier. So U lattice is basically the potential energy of perfect lattice, and this is the mean square displacement, a summation over I to n into Ri minus Ri at 0 whole square. And for each particle, we have to compute that MHD value. So A0 is, I have said earlier, that is it can be evaluated analytically. So to compute the A1, delta A1, we need to perform the MCNVT, because if you perform the Monte Carlo simulations only purely, it will take time to equilibrate. So we will do the MC under MVT. So it will equilibrate the system very fast. So from which we equilibrate by fixing the center of mass, that is Einstein crystal, which allow our particle to vibrate through harmonic spring constant, and it is computed as ensemble average. I have computed over 10 raised to minus 5 configurations, and out of that 10 raised to 500, last 1 lakh I have average to get the proper exact value. And delta A2, that is I have computed for 10 different spring constant. So same ensemble I have used to calculate the delta A2 values also at constant density. And to get that previous integration, this one, I transform that calculated spring constants to transform spring constant to calculate, to apply the Gauss quadrature rule, because Gauss quadrature rule gives better accuracy as compared to other trapezoidal or some other methodology methods. So I do that. So for this transformed spring constant, the mean square displacement is computed using total harmonic energy by dividing it with respect to. So delta bar lambda E dash is the my initial computed spring constant, which I transform to the lambda E, that is transformed spring constant, to apply the Gauss quadrature equation. So here I have used 10-point rule to calculate the delta A2 term in Gauss quadrature. So I need the 10 different values, so I calculate for 10 different values of spring constants. So in this method, using this method, I have computed the free interfacial energy using type 2 interface structure. So it gives for the interface, so which is negative, but it much larger, almost 10, 10 times, I say. So it is very large value, negative one. But the experimental value is 926 millijoule per meter square experimentally for the same system of orientation. So it is not a feasible method for this case. So if I compare all methodology and types of the structure, so I found that the method 2 with type 2 interface structure gives the closest agreement with the experimental values. But for one case, but other case it's more less value. Those values are almost in the same range, but uh, it is much lower. So the methodology overall is not reliable to pick up the anisotropy in the interfacial energy for different orientations of this material. So we use another method. So in which we have the solidified drop. Here the drop is lead system, and that drop we placed at the substrate, and that substrate is the copper. So first we will discuss PB111 clusters. That is, we set cluster because it is nano size atom drop size, nano size. So it is around 16 nanometer diameter drop, which is placed at on the surface of copper substrate, and that substrate size it is 150 cross 150, and that is nanometer. The thickness is 0.7 nanometer on the substrate I have taken. So we perform the NV simulations. So before placing that drop at the copper substrate, we equilibrate separately the drop and the substrate at a given temperature, given finite temperature. So here I have used that temperature 583 Kelvin, which is the experimental value I have for which temperature. So after equilibration of both substrate and drop, I cut the drop to cover the maximum area so that it will stick to the substrate during the simulations, to start the simulations. So the figures is my initial setup for the simulations, that is molecular dynamic simulation. So after 1.04 nanosecond at 583, I have the this structure. So if I resume it, I can see it is spreading slightly. So after so I have three figures here. That is 0.5. We have the spreading also, and relative contact angle I have computed here. So I use the SnapSnake software, which is SnapSnake software, that is contact angle analysis software. It is there. So what it do? It will check all sides of the allowed drop, and it will take the slice, and you calculate the diameter for each angle, and between a drop we have the inclinations. So that
But that is the point. How do you compute the inclination? You have a shape which is locally slightly higher than perfect.
yeah.
So what is the precise angle that is made?
So
just quite here, how do you measure the angle?
yeah. So So we have this. So on all the directions, I have kept many numbers of